Hey everyone, we are Team NASA Camera. My name is Andrea.
My name is Shelby.
My name is Christian.
I'm Pearl.
And we're going to talk about our project today. Our faculty advisor is Dr. Maruthi Akella from the Aerospace Engineering Department at UT Austin. And we have our sponsor, NASA. Chatwin Lansdowne is our NASA and TSGC mentor who's helped us through this project. So we're going to go through our project's background, our objective, our requirements and constraints we ran through, some of the prior art research we've done, our design solutions and evaluations of those solutions, our engineering analysis, and lastly, our conclusions.
So I'm going to start out talking about our project background. And so the context of the problem that we're examining today is that NASA has an obligation due to its mission of education and not advancing knowledge to capture video of astronauts working on the moon. But this video is extremely difficult to capture as astronauts have so many tasks to complete in such a short amount of time that taking up a whole astronaut to just video record and take pictures is a potential waste of time for where they could be working on other tasks. And the lunar environment is very relevant because NASA, through the Artemis program, is hoping to land the first woman and next man on the moon by 2024. So our project is to explore the feasibility of using a camera drone in this lunar environment. And if it's proven feasible, or we can come up with different ways to make it feasible in the future, a lunar drone would allow astronauts to focus on these other important tasks while still capturing video and photo evidence. And so just some background on camera drones in general. So they've been used both on Earth and in space. And on Earth, I think most people are familiar that they use 4 fans to propel and maneuver. And the main constraint to flight time is battery capacity. In space, there have been multiple successful drones that have been used both inside and outside of the space station. Most are propelled by nitrogen gas canisters, and the main constraint is the amount of propellant that was brought up. And then in the lunar environment, it's a completely unproven concept where we've determined the main constraint is going to be the weight of the drone and propellant.
Problem statement. So this is our problem objective. We are aiming to complete a feasibility analysis prototyping of a camera drone platform that can follow astronauts on the moon. And at the end, we are going to be describing the technology and the materials that is required to make this product. And we also researching other patents that may be creating similar lunar technology. Our main focus has been utilizing lunar regolith as a propellant of the drone. The key to the feasibility of this concept is how quickly and efficiently you can accelerate lunar regoliths.
Requirements and constraints. So the only quantifiable design requirements that we have for the function of our drone is that it needs to be able to fly and record for at least 20 minutes, and it needs to be capable of carrying at least 100-gram payload, which for our case will be a camera. Other than that, we seek to minimize the size, weight, and power requirements of the drone so that NASA can cheaply manufacture them and bring them to the moon. And it needs to be capable of operating in a lunar environment. So that would include withstanding intense radiative heat and being able to survive in the lack of atmosphere. Now our spec sheet. Most of the variables couldn't be determined since they're all so intrinsically linked together. For example, the weight, power, and thrust are all very, very closely tied together. If you can make the weight lower, you can have less thrust and therefore require less power. So really it all depends on the type of materials that we use and how low we can get the main weight to reduce the cost of transporting and building the drone.
Prior art. So the table on the left side are the possible propellant, propulsion, and power methods that we have been referring to as we develop our project. For propellant, we found 2 patents. For propulsion, we found a patent that describe a design of an electrostatic ion thruster that can work in outer space. And for power, we have 3 other options, as you can see in the table. On the right side, we also study the previous applications of drones used in outer space. These drones have not been functional or used in lunar environment yet, but we did study the previous design of a specific example, a sprint camera platform. This device released nitrogen gas from a pressurized canisters to keep the drone aloft. This influenced us to study the use of pressurized gas in conjunction with lunar regolith.
Next, I'm going to talk about our design solutions and evaluations. Our decision-making process began with background research and structured brainstorming for what solutions we could think of. Then we considered some further research on the feasibility of each of those solutions and calculations, which then fed into our pew chart, which is a way for us to have a comparison of design options with the values that we were coming up with from our calculations. And the results of this pew chart gave us the potential solutions for feasibility. So this is an example of one of the pew charts we made. We were comparing 3 different power sources, which are nuclear, lithium ion, and a solar cell system. And then we also had a pew chart for propellant, which those options were lithium hydride, nitrogen gas, and accelerating lunar regolith or lunar dust. So what we found after considering all of the power criteria and propellant criteria, which mainly was size, weight, safety, and more, we came up with the final results that we should continue looking into lithium ion as the power source and lunar regolith as our propellant method.
For our engineering analysis, we decided to take a deep dive into the feasibility of the lunar regolith concept. So since our design will need to carry its own propellant, the drone will be governed by the rocket equations. So using the ideal rocket equation on the bottom right there, combined with a known thrust value that we know we'll have to achieve, we were able to find preliminary values for our lunar regolith mass and exhaust velocity requirements. These are those results. One thing to keep in mind is that these results are for an empty weight of 2 kilograms. So this assumes that the platform of the rocket and the payload of the rocket are included in that 2 kilograms. Other than that, we have the properties of the lunar regolith and some geometrical constraints on our rocket and nozzle. You see that we require a propellant velocity of 295 meters per second to maintain flight for 20 minutes with a propellant mass of 13 kilograms. I would like to add that that's quite heavy and quite fast. So maybe already this is looking not to be feasible. Next, we created a simulation. We were able to track the loss of propellant mass over flight by adjusting the exhaust velocity continuously based on remaining propellant. Basically, what that means is as the mass of the propellant was lowered over the course of the flight, we adjusted the exhaust velocity to slow down to compensate for that, so that a hover state is maintained on the moon. And here are the results of that simulation. As you can see, in this example, we started with 10 kilograms of propellant, and it seems to last us about 9 minutes, which already I think 10 kilograms is probably too much propellant that would be feasible, and it only lasted us 9 minutes. So it will likely not be feasible for long flights.
So moving on to our conclusions. As mentioned, we examined the feasibility of multiple concepts and then down selected and did a deep dive on lunar regolith. And as Christian mentioned, we've determined that at this time, lunar regolith is not looking like a fully feasible option for meeting the design requirements, specifically the flight time. We have our hopeful lithium ion batteries would work as a good power source. And our research so far has shown that that is true. And just as a example, we've also looked at pressurized gas and determined that's even less feasible than the lunar regolith would be. So the next steps to finish out this project are to identify the needed parameters for lunar regolith to potentially be feasible for in the future. And then the next steps for this project as a whole, if it's chosen to, research is chosen to continue to be done, will be designing the storage, propulsion, and platform for a drone that would use lunar regolith as a propellant. Thank you, and I guess now we're open for any questions.